Hello students, welcome to the video lectures of speech and natural language processing. So today we are going to talk about hidden Markov model and maximum entropy models for named entity recognitions. So named entity recognition is a crucial task in NLP that involves identifying and classifying named entities in text, such as persons, organizations, locations, dates, etc. So both hidden Markov model and maximum entropy models are widely used for named entity recognition due to their ability to capture sequential information and incorporate various linguistic features. Let's explore how these models function in the context of named entity recognition. So primarily named entity recognition, for example, if I say Apple is going to launch a new iPhone, I mean, let's say iPhone 17 in 2025 at California, let us say. So in this particular sentence, Apple is the organization name, iPhone is the product name, 2025 is the year, that is time or year, we can say. And finally, it's California, it's the location. So for a particular sentence which is given, it is necessary to identify to what entity it is referring to. So in order to identify these named entity recognition we call for a particular given sentence, we incorporate hidden Markov models and maximum entropy models. Let's see how they hidden Markov model. So that is HMM we call. So in our previous video lecture, we have seen hidden Markov model used for parts of speech tagging. Now we are seeing hidden Markov model for named entity recognition as well. So hidden Markov model, that is HMM, is a probabilistic model that assumes the data. So in this case, that is our NER case, words in a sentence are generated by a hidden sequence of states which correspond to entity labels such as person, location, etc. Each state emits an observable word with a certain probability, which means, let us try to understand this with the example what I told you in my previous slide. There I told you Apple is going to launch iPhone so and so in 2025 California, right? So there, the things what you observed in the sentence, okay, that are, so in this case, words in a sentence, probabilistic model that assumes the data, in this case words in a sentence, are generated by hidden sequence of states which correspond to entity labels. So these are all the hidden entity labels. Each state emits an observable word with a certain probability. So now for the given sentence, it will try to identify the to what entity it belongs to. So hidden Markov model works for how HMM works for NER. The HMM based NER model tries to find the most likely sequence of named entity tags that could have generated the observed sequence of words in a sentence. So components of HMM for NER. First one is states, that is tags. So in named entity recognition, the states are named entity tags such as PER, which stands for person, ORG, which indicates it's an organization, LOC, which indicates a location, O stands for other named entity. So in any hidden Markov model, we have these emission probabilities and transition probabilities. So emission probability is the probability of observing a word given a named entity tag. For example, the emission probability of observing John given the state is person is high, obviously, right? And transition probability, the probability of transitioning from one named entity tag to another named entity tag. For example, transition from O, that is not a named entity, to a person might be high at the start of a sentence. Whereas the transition from person to location might be low in typical English sentences. This is that. PER stands for person, LOC stands for location. So initial state probability, the probability of starting with a particular named entity tag, such as O at the beginning of a sentence, that is other named entities. So when we say this hidden Markov model, so basically what happens in this hidden Markov model, we already discussed in previous tagging as well. So basically, there are some observable, things by which we try to predict the hidden things. Okay, For example, I'll just tell you that you are just sitting inside a room and you are just trying to make some prediction by observing some events. Let's say a person is entering into your room with an umbrella. Then the probability, you might think that the person is having that umbrella because there is some rain outside, would be some 70 to 80% probability, and the person is carrying an umbrella because the weather is very sunny outside. I mean, weather is very hot. So there are two things which you can assume now. So one is having higher probability, the other is having lower probability. The higher is it's been raining. The lower is there is the weather is very hot. So in such a way, so observing some events, you are trying to predict some other thing, right? So these are such probabilities. And if suppose some other person, let us say this condition of hidden macro model can be applied for some weather prediction as well. So coming to weather prediction, suppose if there is a heavy rainfall today from the morning to evening, so the probability that tomorrow also it rains would be more. That is some around 60-70% might be sometimes. And the chances that tomorrow it will be very hot would be somewhat less. Tomorrow it would be cloudy is moderate, right? So this is how hidden Markov model works. Basically, if there are three events, let us say A, B, C, and C is the prediction on the next event, what we are trying to say would depend on the previous B event, but not any other event, that is A or some other external events. Clear. So that's how hidden Markov model works. So assuming the probabilities, and we just try to have these emission probabilities and transition probabilities. Next is maximum entropy models. So maximum entropy models, MEM, is a discriminative model that predicts the most likely named entity tag for a word by considering all available contextual features without making strong independence assumptions. MEM aims to maximize the entropy of the model by making a few assumptions as possible, ensuring that the chosen model aligns with the training data while remaining unbiased about things not explicitly learned. So how does maximum entropy work for named entity recognition? This does not assume that the current tag depends only on the previous tag, as in hidden Markov model, as I told you, allowing for more flexible modeling of dependencies. It can use rich, non-local features to improve predictions. So what are components for named entity recognition through maximum entropy model are features. So MEM allows the use of arbitrary features to predict the named entity tags. Features can include the current word and its surrounding words, parts of speech tags of neighboring words, capitalization. Example, you can see in the name John, J is capital. It starts with a capital letter, suggesting it might be a person's name. Next is word prefixes and word suffixes. So words ending in -ville, that's Willie, are likely locations. Whether the word appears in a known entity list, that is example known list of organizations or locations. Next is conditional probability. So maximum entropy model directly models the conditional probability of a tag given observed features. So the model chooses the tag that maximizes the probability based on the given features. So how does this work? It does not assume that the current tag depends only on the previous tag, allowing for more flexible modeling of dependencies. So it can use rich non-local features to improve predictions. So this is the example. So now let us consider the sentence. John works at Google in California. Now you can see there are a couple of things in this. So different parts of speech, primarily to say there's a noun, there's a verb, there is a different kinds of things. So and name entity recognitions are also different. There's a person, there's an organization, there is a location, etc. So MEM based NER model would use the following features. For John, the capitalization of the first letter, since you can observe J is capitalized in this, it predicts that it would be a name. So its position at the word beginning of the sentence. Previous tag, neighboring words, etc. Works, etc. The Google, so word capitalization, previous tag, surrounding context work set, and the fact that Google might be in a dictionary of organizations. So based on these features, maximum entropy model will output the most likely named entity tags. So John could go for person, workset will go for organization, Google is organization, in is other, workset is other, sorry, not organization, California is location. Okay, students, hope you understood. Thank you.